All right, welcome to The Explainer. Today, we're diving into one of the most powerful tools in economics, the Lagrange multiplier. Think of it as the mathematical secret for making the absolute best choice you can, even when your options are limited. So here's the game plan. We're going to start by really understanding the core problem we're trying to solve. Then, we'll introduce the super elegant tool for the job, the Lagrangian. After that, we'll uncover its deeper economic meaning, figure out how to make sure our answers are the real deal, and finally, see how this whole method can scale up to tackle even bigger, more complex problems. Okay, so first things first. What kind of problem are we even trying to solve here? Let's break down the fundamental challenge. At its core, this is all about constrained optimization. It sounds fancy, but it's something we all do. Imagine you're a consumer trying to maximize your happiness, what economists call utility, but you've only got a certain amount of cash in your wallet, right? You can't just buy everything. You've got to find that perfect sweet spot, that combination of things that makes you happiest without breaking the bank. To really get a feel for this, think of it like this. Our function, f of x and y, that's like a giant mountain range. Our goal is to get to the highest peak possible. But there's a catch. Our constraint, g of x and y equals c, that's like a specific trail or a path that we are forced to stay on. We can't just climb straight to the top. So we're looking for the highest point we can possibly reach while staying on our designated path. And where does that happen? It happens at the exact spot where our path just barely kisses or is tangent to the highest possible elevation line, what we call a level curve on that mountain. Any other point on our path would put us on a lower, less optimal level curve. And that right there, that visual, gives us the crucial mathematical rule we've been looking for. At that one perfect optimal spot, the steepness of our path is identical to the steepness of the mountain's contour line at that point. Their slopes are equal. And that simple fact is the key that lets us build a formal method to find this point without ever needing to draw a map. Okay, so graphs are great for understanding the idea. But how do we actually find that magic point using just algebra? Well, that's where the super elegant Lagrange method comes into play. What we do is we build this new special function. It's called the Lagrangian. And what it does is really clever. It merges our original goal, our f of xy, with our limitation, our g of xy, all into one equation. And in the process, it introduces this new, incredibly important variable, lambda, the Greek letter lambda. We call it the Lagrange multiplier. And the beauty of this is that it's basically a 4-step recipe, super systematic. You just write down this new Lagrangian function, take its partial derivatives and set them to 0, throw the original constraint back into the mix, and then solve the whole system of equations. It's a process that magically turns a difficult constrained problem into a much more straightforward algebra problem. All right, enough theory. Let's get our hands dirty with a classic example. Let's say we want to maximize the area of something, which is just x times y. But we have a constraint. Maybe the resources to build it, represented by 2x plus y, are fixed at some total amount, m. So how do we get the absolute biggest area possible? Okay, step 1, just like our recipe said, we build the Lagrangian. We take our objective, xy, and we subtract lambda times our constraint, which we've just shuffled around to equal 0. And just like that, this one equation now holds every piece of information from our original problem. Next up, the calculus part. We find the point where this new function is totally flat by taking its partial derivatives for both x and y and setting them to 0. Think of it like finding the very top of a dome. These are what we call our first-order conditions. Then we just add our original constraint back in, and all of a sudden, we've got a tidy little system. 3 equations and 3 things we need to find, x, y, and our new friend, lambda. And finally, we just solve it. The algebra spits out the perfect values for x and y, all in terms of our original constraint, m. But wait a second. Look what else popped out. We got a value for lambda. And let me tell you, that little guy is way more than just some mathematical leftover. It's actually one of the most powerful insights of this entire method. So what's the deal with this multiplier, lambda, anyway? It's not just some number we needed to find x and y, no. It has this incredibly cool, super useful economic meaning. Remember in our example we found lambda was m over 4? That's not just a random fraction. It's telling us something really specific and powerful. Here it is. Lambda tells you exactly how much your maximum value, your best possible outcome, would increase if your resources, m, went up by just one single unit. It's the value of getting just a little bit more wiggle room. It's the bang for your buck if you could loosen the constraint. And this is why economists have such a cool name for it. They call lambda the shadow price. If your constraint is a budget, lambda is how much more happiness you'd get from an extra dollar. If it's a limit on production, lambda is the extra profit you'd make if you could produce just one more item. It reveals the hidden economic value of the constraint itself. Okay, hold on a second. We found a flat spot, which is great, but how do we know for sure it's a peak, a maximum, and not the bottom of a ditch, a minimum? We need to be absolutely sure we found the best case scenario, right? How do we double check? Well, to figure that out, we have to check what's called the second-order conditions. We use a tool for this called the bordered Hessian. Yeah, I know, it sounds super intimidating, but the basic idea is actually pretty straightforward. It just looks at the curvature of our function right at our solution point to tell us if we're on a peak or in a trough. And after all that math, the rule itself couldn't be simpler. You just look at the sign of the final number you get from the Hessian. If that number is positive, congratulations, you found a local maximum, a peak. If it's negative, you found a local minimum, a valley. It gives you a clear, unambiguous answer. But here's where the Lagrange method goes from a neat trick to an absolute powerhouse. It's all about how well it scales up to handle much more complex, real-world problems. The amazing thing is, the logic we just walked through, it works whether you have 2 variables or 2,000. And what if you have more than one constraint, like a budget and a time limit? No sweat. You just add a new Lagrange multiplier for every single constraint you have. The system of equations gets bigger, sure, but the fundamental method stays exactly the same. All right, let's do a quick flyby of everything we've covered. We started with this core idea of constrained optimization, finding the best possible outcome when you've got limits. We saw how the Lagrange method is this amazing recipe for turning that hard problem into a solvable system of equations. We unlocked the secret of lambda, the shadow price, that tells you the value of relaxing your constraint. We learned how to use second-order conditions to confirm our solution is a maximum. And finally, we saw that this whole tool is totally generalizable for really complex problems. And you see, this isn't just some abstract tool for economists. It's a whole new way of thinking about the trade-offs we all face every day, from our personal budgets to huge public policy decisions. So I'll leave you with this thought. Now that you have this powerful new lens, what real-world problem of choices and constraints would you want to solve first?